Now, the topic of today's talk is deep learning with IoT. Now, why are we thinking of such things like deep learning with IoT? The basic background behind this would be like when we think of pushing some amount of storage and processing capabilities at edge devices. Naturally, we would also want more powerful algorithms to run there if possible and see how they work at the edge devices. So this is the direction I would like to go in future. So today's presentation will give you theoretical pointers to work in those directions. Of course, I've implemented some small deep learning models on Python on IoT, but image processing and natural language processing and speech recognition, those are not my frontiers. I work with some healthcare informatics data. So I hope I'll start with the screen sharing. So yeah, just a second. Or press Alt F1. Yeah, okay. My screen is better visible now, I think. So this will be the organization of presentation. Like almost all of us have written programs during our college days, and we would write programs on a desktop. But as we move to industry or as we had more exposure of the real world, we realized that programs on their own don't mean much. If they are written as part of a network, that will be more towards the real world. During those days, gaming programs would be written on a desktop, but nowadays even we have online gaming platforms. So the basic premise of all these technologies, I would start with cloud computing. Then I would see that edge and cloud computing, are they mutually exclusive or do they complement each other? That will be the next point of discussion. Then IoT as a edge computing device, a gateway, right? Under that category, I would take Raspberry Pi 4. Then through this Raspberry Pi 4, how does it help in going with cluster computing? Then a brief introduction to deep learning. Then what is distributed deep learning and in which futuristic direction are we heading to? So this is the way I'll be going. If there are any questions, you all can put on the chat window and the organizers can alert me, or you can even use the audio to interrupt. So we all know what is a cloud computing, right? So we say that let's minimize. Uh, just I'll say cloud computing is an on-demand availability of computer systems resources, especially data storage and computing power without direct active management by the user. So we sign for certain resources, right? And those resources are automatically provided and managed by the cloud service provider. So a lot of these activities which the end user or his organization would do is now moved to cloud. Now, the term is also generally used to describe data centers available to many users over the internet. So, what are the large clouds that we predominantly have today? Have often functions distributed over multiple locations from central servers. So, if the connection to the user is relatively close, it may be designated as an edge server. So, here we come across a term called as edge. And for any computer to be scalable, it is but natural that it needs to function in a distributed manner and delegate tasks to some powerful nodes. And these nodes, we call them as the edge devices. Okay. So a brief introduction. What are the advantages of these clouds? We all know that ease of implementation, that whatever applications the user would have visualized he needs in his enterprise can be easily put on a cloud and provided as a service to him. Accessibility, now with internet being predominantly used in almost all organizations and to individuals, we can access these resources anywhere, anytime, but with a pinch of salt like security. And there is no hardware required since most of the resources will be hosted in a cloud. So a physical storage center is no longer needed. Like we set up a server, we provide storage space to it, we provide cooling facilities, we need power facilities with a backup for 24 bar 7, and we need to have a lot of these management things that we need to take care when we put resources, because everyone assumes that once a resource is available, it is available to him by default. No one will tolerate downtime. This has been witnessed by me because I set up a Moodle server. I facilitated setting up a Moodle server in the institute where I'm working, and now people want it 24 bar 7. If the server goes down because of some issue, we get mails from students, we get mails from staff, Moodle is down. They don't understand, like maybe the SSL certificate has expired, or the backup power also exceeded, or there were any other issues. People don't want those such issues. Then cost per head, right? So we can think of competitive costs when we try to host on a cloud, because there should be some cost benefit analysis to be done, because we are speaking of a scalable technology like cloud. Then there is flexibility of growth. This was the greatest challenge. Like now, if I have to upgrade a server, I have to increase the RAM, I have to go from SATA hard disk to power drives, right? I have to make a host of changes so that I can a more number of users can hit. I need to increase the RAM and all these facilities. But when we have a cloud, scalability of resources is taken care by the cloud. We have a efficient recovery plans. We can buy plans where we have backup and we can recover the same, of course, by burning a hole in the pocket. There are certain disadvantages whenever we propose something has to be moved in cloud. People argue like, look, you are no longer in charge of your data and information. It is going to be shifted to cloud, right? We have different service providers, and all of them may not provide the same set of features. Some may even provide a most popular features and may just keep the other features in a more requirement based kind of scenario. They may facilitate the use of those features. So parity among all the cloud service providers in terms of features is a big issue. So what does it mean, right? So it doesn't mean that you have to let go your servers, because if maybe let us assume that if the cloud is a single central point of failure and if all our data gets lost, let us assume a hypothetical scenario, we would not like all the data of our organization to just vanish. We could have some recovery and backup in our own data centers. So that's why I said having a redundancy on a cloud will also have cost issues, and bandwidth is another major issue, because the client may try to pack a lot of amount of information on small data servers, and this may result into a host of bandwidth issues. So of course, though there are advantages, there are disadvantages. So what are the critical questions I feel when I think of migrating my data, especially if you look at the medical informatics that is there in organization, there are that is there in countries like US. They have their data protected by laws, and privacy comes into a picture. So when I'm moving my data outside my hospital or outside my organization, I always have a question that will my data be secure? The next thing is it truly accessible anytime? Like we all know from our telecommunication domain, that in the long old days of landlines, we used to have a availability factor of 99.96%. What did it mean? It means that 0.04% of time the network would fail. So when we want to access a particular service, and if that service is not available at that time, reliability becomes a big issue. So what happens if the cloud fails? Usually we see such limited scenarios in news, but recently we saw that some Google Cloud services were becoming slow or were not becoming available. These are rare occasions, but they still exist. Now, will my provider ensure that I'm getting top performance of cloud services? Can I get an opportunity to test the facilities that he has provided and benchmark and see that the performance levels and the benchmark testing are meeting all the time? Do I get such a facility? These are some of the aspirations or doubts that come into our mind. Will I be able to move applications and data around seamlessly? And is it accessible from anywhere? Like suppose I want to migrate from one place to another. what are the APIs they provide, and how are the accessibility features from anywhere. These are some of the doubts that come when we try to migrate to cloud computing. So, these initial slides, apart from the questions that we ask, cloud computing, along with the Internet of Things and along with data science, I believe these are the three pillars that are driving the growth engine of computer science and its allied branches. So cloud computing is a very great phenomena. It is there to exist and people are going to use it extensively. There is a huge potential for growth in this direction. Now, how are we going to optimize it? Or how are we going to complement this cloud computing so that we move in a better direction? Is there a device or a computing technology called as edge computing that's involved? So a brief background, like why do we need edge computing? Like all of us know that the internet version 2 speaks about, or internet 2.0 speaks about connecting internet to devices, objects or things. Internet 1.0 spoke of connecting internet to humans. Now we are speaking of connecting internet to device, objects or things. What do these things or sensors do? They produce a huge amount of data. They produce a vast amount of data. And what happens when these, like we all know this when we studied sensors. Sensors are tiny devices which collect the data and relate to aggregator devices. These aggregator devices in turns aggregate the information and send it to a central server. The server would process it. So these small tiny sensors produce a huge amount of data. And this data, like under our topic of discussion, we are assuming IoT devices is being generated and they are being relayed to a central network server, usually housed in a data server. Now, once that data is processed, further instructions are sent back to the devices out on the edge of the network. Now, there are two problems with this setup. First is that it takes a lot of time to travel from the edge device back to the center. And though this delay may be in milliseconds, it may be still critical, right? We don't tolerate a delay of few microseconds. If we hit www.google.com or gmail.com and if the web page doesn't flash back to us in few microseconds or even less than that, we don't have patience to tolerate it. We just move to another mail service provider. Secondly, all the data that is traveling back and forth between the edge and the center of network put a tremendous strain on bandwidth. So each node or each device is producing huge amount of data and that is traveling to the central server. That's basically consuming a lot of bandwidth. So we need to optimize this in some way so that we cut short this travel and place devices on the edge of the network, which can do some amount of work that would have been normally been done at the central server. So what is this network latency, which is a major issue? So it tries to calculate how long it takes for a data packet to travel from the origin point to its destination, and these can have serious consequences for IoT devices. For example, self-driving cars, right? If there is a delay in taking some critical decision, we know that it may be a matter of life and death. So edge computing offers a solution to the latency problem by relocating the crucial data processing to the edge of the network. Personally, I feel there are two advantages. One, like I spoke, like aggregators, these can increase the granularity of the data so that cloud central uh, central machine learning algorithms working in the central device can process it in a more quicker manner, right? And the second thing over here is, like, if we are speaking of some organizations where privacy of data is very critical, right? We can have powerful edge computers which manage most of the things, and for very minimal dependency, they can take of the help of the central computing facilities. So, what is the takeaway? Rather than constantly delivering data back to a central server, edge enabled devices can garner and process data in real time, allowing them to respond faster and more effectively. So, when used in tandem, so the underlying, so first we came up with cloud computing. We said it's a very important technology. All of us agree. Then we moved to edge servers, and now we are coming up with a concept that this should be used in tandem. That is, they should complement each other and take the advantages of their processing capabilities, so that they complement each other, like in terms of storage or in terms of computational processing capabilities. So they work in sync. So if I look from IoT and edge computing device. So as I said, a cloud computing will gather all the data and process it in a centralized manner. Since everything is centralized, the cloud is it's easy to secure and control while still allowing for reliable remote access. So the major cloud computing services we have, such as Microsoft Azure, Amazon Web Service, Salesforce, Google Cloud, they provide a tremendous benefits for organizations that would traditionally depend on the client server network. Also, buying servers nowadays are pretty costly, and the way the computing power is increasing and more number of cores that are fitting on the processor, right? It can quickly become redundant, and installing a lot of money on server becomes questionable to organization. So by storing assets and information in a cloud, they ensure that authorized users can access the information from anywhere and anytime. So finally, what we do, we try to select the best of edge and cloud computing, right? So we should not say they are mutually exclusive. We should assume that they traditionally help each other, right? This is basically because of the boom that is taking place with Internet of Things devices. Okay. Now, so is cloud everything? How our edge computing devices or things. Now, being computer science engineers, we usually think of IoT in terms of a Raspberry Pi. A Raspberry Pi is a small computational device, right? Handheld computational device that can provide us powerful processing capabilities. Later down the talk, I will show you what's a Raspberry Pi. Most of you already may be aware, but if there are some student delegates who would like to know about it, it would be useful. So Raspberry Pi is you can classify it more than as a IoT. You can classify it like an IoT gateway. Okay. So what are IoT gateways? They are essential components in building a robust Internet of Things and for delivering computational power in edge computing scenarios. So what do these scenarios do? That is, they distribute the load on system by performing data processing at the data source on edge rather than relying on the central server for bulk of the work. So this IoT gateway is a solution for enabling IoT communication in terms of device to device or device to cloud communication. So a simple way to conceive an IoT gateway is to compare it to your home or office network router or gateway, right? So these devices facilitate the communication between the devices, the gateway, and the internet. So similarly, we have a IoT gateway, but it can do much more. So this is the scenario. We have a internet, right? And we have a IoT gateways, right? And we have the sensors. We have sensors placed on huge number of devices. This information go to these gateways. They collect the information, increase the granularity of the data, and pass it on to the internet, right? So i have a I have a interesting question to all of you. Hope delegates are still there, right? I will type it in the chat window. If somebody is there, please answer. What is the difference between internet and internet? So I have posed a simple question. You can open the mic or you can answer in the chat window. I want to know what is the difference between internet and internet.
Hope everyone is able to hear the speaker, because at least Gajendra, myself, Karthik, and Megan, we are speaking. But what about others? Are they really able to hear?
Yeah, I would like the feedback from the organizers. Am I audible?
Yes, sir. You are audible, sir. No
We can
problem.
hear you, sir. We want
Huh.
to ask others.
Yeah, yeah. So what is the difference? Like there are some interesting questions. Like when I saw that internet diagram, I thought like, is there any difference between capital I and small I? Is it more of English or it has to do something? Yeah, one is Karthik Kumar Chaudhary has answered. One is complete internet as a class, and another is a subset, a network of a network, right? Yeah, yeah. Karthik is he has tried to answer it, right? So the capital I is the public internet, which we know, the internet that is known across the world. We call it as a WAN of WANs or a network of networks, right? It is based on the TCP/IP standard, and it's a huge public network. That's the capital I. A small internet is more of a kind of you can think of like a intranet, right? And yeah, someone else also has given an answer. Lowercase I refers to any that are connected to yeah. Uppercase I is the public internet. See, nowadays what happens in olden days, we used to have networks with different protocols. Like before TCP/IP came, there were huge number of networks. So the current style is, even if you design a LAN, it should be of TCP/IP standard, and it will be integratable to the internet, right? So if we have a small network or like corporate network or a campus network, right, which is meant for our own this, we can call it as the small I. This or a large network, data communication network, small I. The public network is called as the capital I. But mind you, even in some very standard newspapers, like if you take the Hindu and all, when they refer to the public network, that is the internet, they still use the small case. This is an error that I've noticed in almost most of the literature. So through this medium, I would like to say that whenever you come across such doubts, you can clarify. So this was about IoT and edge. So as I said, like Raspberry Pi, I would consider it as more as a edge computing device. So monitoring, analysis, prediction, and control, like we can all perform this with IoT device like Raspberry Pi, and we can call it as a things or a internet gateway, right? So a Raspberry Pi with sensors connected to it does provide the things with the internet gateway. Now this Raspberry Pi had its origins in UK, where the originators wanted to develop a small size affordable computing devices for schools and other people. And with this, the pocket size computer came up with, right, or a credit card size computer came up with. And naturally, when IoT was being thought about, like sensors, people had started placing cameras, people had started placing temperature sensors to monitor the network infrastructure, right? A host of these sensors had started coming into our homes, neighborhoods. And naturally, they thought like these devices can collect the information and send it to some central processing facilities, and it came into a right picture. So most of the times I work with Raspberry Pi, right? So it is a ARM based processor, right? And this ARM stands for Advanced Risk Machines. All of you know risk machines, right? Again, my next question in the chat window would be, right, uh, which is better? Like, which is better? Like, would you look at CISC? Would you prefer CISC or would you prefer risk? CISC or risk? So which one would you prefer? Like if you have a laptop, like I'm using a laptop, is it based on CISC or is it based on risk? Or what are their relative advantages and disadvantages? Sometimes a nominal chat between our presentation is better for speakers also. Like we can relax a few seconds, and also if there are very highly learned audience, they can answer, and that makes us feel satisfied. Like so, or it may be a very basic question. In that case, forgive me. So, so anybody would like to venture to answer the previous people who had answered? Amit R, Karthik Kumar Chaudhary, Shankar. Yeah, I have received a message. Yeah, Karthik Kumar Chaudhary says risk is faster than CISC. I feel absolutely right. He is absolutely right because CISC has a different goal. CISC says complex instruction set means the operands that are there, not the operands, the instruction set are more complex in nature. They can perform more complex instructions and they are more closer to the languages like our high level languages which emphasize on more complex instructions. Risk relies more on the registers that are available near the CPU. Instead of storing a lot of information in the memory, they rely on registers. So risks are faster, but there is a limit on number of registers you can put. So most of the powerful computers are CISC, but risk is also, see, gone are those days when we would say that this philosophy sticks only to this philosophy sticks only to this. Like when I migrated to Python language from C language, I felt there are so many things in C which would be very cumbersome to do, are managed in a very simple manner in Python. So it is a language like people who migrate from C to Python, they would like to work in Python. So similarly, the RISC board 4 is coming up, which they claim is a very powerful device. It is still in a board fashion, and some US organization has got a patent for it and is manufacturing. Those boards are available to educational institutions and all. So we can experiment on those devices. So our Raspberry Pi is based on a RISC machine. So what it emphasizes the use of registers, smaller instructions, and can achieve higher speeds with the capability of executing millions of instructions per second, or we call it as MIPS. Just a second. Okay, just a second. So MIPS, yeah. Okay. So what happened here is we came up with Raspberry Pi 3B, which was 3B, 3B Plus, which was still recently considered as the one of the latest versions. It was based on Broadcom BCM 2837 processor. It had 1.2 gigahertz clock frequency, and it was 50% faster than the Raspberry Pi 2 model. But in 24 June 2019, Raspberry Pi Foundation launched Raspberry Pi 4. So what it has a 64-bit quad-core ARM Cortex processor, BCM 2711 CPU, and it is running at 1.5 gigahertz. So I have a old desktop, I think, which has around 1.2 gigahertz or maybe 2.1, and these Raspberry Pi devices are slowly capturing it, and it has a range of memory options like our mobile devices, 1 GB, 2 GB, 4 GB, and they are using DD4 RAM, which is quite faster as compared to DD2 RAM. So the new processor, when paired with 4 GB RAM, is able to deliver something closer to our desktop class performance. So CPU heavy tasks like game emulation and all those things, right, can be easily achievable by from Raspberry Pi 4. So this is a diagram from Raspberry Pi 4, right? And it boasts about USB 3. Here you can see the diagram, USB 3. It has a gigabit Ethernet, right? Any general question again, when I see some networking concepts, I feel of asking questions. For Ethernet, Ethernet, uh, we all need high speed computing. So Ethernet versus which technology, right, are computing for high speed networks. So one is Ethernet, we saw. Can anybody tell, is there any other technology which competes? Both of these are computing to provide high speed, like 1 gigs to 10 gigs, right? Initially, we used to have a 100 bar, 100, 150 bar, or 200 Mbps, and so on. Now we are speaking of 1 GB. Yeah, Wi-Fi and 5G. Okay. Hmm. Okay, you have moved into the wireless domain. I would, when I'm speaking a network, I'm still restricting fiber channel. Okay, fine. We usually traditionally we have a network called as ATM, asynchronous transfer mode, and these with the combination of fiber were considered as very high speed technology driving the networks, like your banking ATMs. They need to process the transaction in a very high speed manner. So these were the technologies that would complement it. Ethernet is also trying to come to that level. So most of our Ethernet cards that we have are around 1 GB, right? So your Raspberry Pi provides 1 GB. We discussed about a new powerful processor. We have a USB-C power supply because a new processor and USB 3 and all these devices require more higher means appropriate power supply. Recommended is to go to the Raspberry Pi for official power supply, because we take a chance if we try to supply to some Android charger and all that, right? Then we have two micro HDMI ports. Now my question here is, again I go to the chat window. Why two two HDMI ports? Why two? The question is obvious. Anybody would like to involve themselves? Bhatkande, Amit, Karthik Chaudhary. Okay, with this you can connect to HDMI. Yeah, someone message. So with this, yeah, yeah, rather than multiple sources, we can say that two monitors you can connect at the same time, or you can mirror and all those stuff. USB 3 gigabit. So this is a very powerful device that has come up with. So the story goes so far here is cloud is there to stay. Cloud can be optimized or complemented by using edge devices, and Raspberry Pi is a promising device to build a edge computing device. Advantages are lower cost of bandwidth. If with some data storage capabilities, if we can generate sensitive data, can be within the premises. We need not worry of the data traveling. More computationally intensive, right? On generic data can be performed in the centralized storage. These devices, right? So slideshow from the current slide. Okay, so this was about it. So as I said, ARM stands for Advanced Risk Machines, right? And reduced instruction set computer. So RISC emphasize the use of registers, smaller instructions, like as I said, complex instructions were for our CISC machines, and the smaller size of ARM processors, low power consumption, make them most suitable for miniature device like Raspberry Pi. So these are some old slides where I've picked up. Raspberry Pi 3B uses 1.2 gigahertz, but our Raspberry Pi 4 is based on 1.5 gigahertz. So what is the significant difference is the ARM Cortex A53 cluster, so which makes it very fast. Okay, so now we'll come to see what are so good about this Raspberry Pi board, because now we are heading towards building a edge computer. So what is so great about this Raspberry Pi board, right? So it has a there is a linpack test that is carried out. So this test goes into three variants: the fast single precision SP, slower double precision DP. We have this linpack library. It is based on Fortran. We can install it and run these benchmark tests to see how Raspberry Pi 4 compares with the older versions of Raspberry Pi. So why I'm speaking so much about Raspberry Pi is, now we are trying to think about a device which is cost effective, which is powerful, and which will help us to build towards a powerful edge computing device. Okay, powerful and cost effective. So the third test is single precision variant accelerated using Neon instructions. So you can just note down this linpack library, right? Now, before I go to the test, glorification of the processor that Raspberry Pi 4 use. As I said, it uses BCM 2711 with 4 CPU cores and a clock speed of 1.5 gigahertz. And people may say it is what's so great, like Raspberry Pi B3B plus uses 1.4 gigahertz and this uses 1.5 gigahertz. The difference is this Cortex 72 has 15 instruction pipeline depth compared with just 8 on the older model. And it also provides something interesting which I have not ventured out, that is out of order execution. So it's not waiting for the output of one of the process to start another. So these are some of the benefits we have, right? So these Cortex A72 processors will be significantly faster, but the downfall is they use more power than their AS53 powered ancestors. So we have this Linpack benchmark for SP and single precision and all these things. So you see SP, DP and SP neon. Just look at the rightmost corner, you see Raspberry Pi 4, right, has overwhelmed all the previous ancestors. They are nowhere match. Even Raspberry Pi 3B plus doesn't come anywhere near it. So we are witnessing phenomenal technology in terms of Raspberry Pi 4, and this is going to continue. It is going to continue in building more powerful devices. And as I said, they are based on DDR4 RAM, which obviously increases the speed, right? And we have a Broadcom Video Core 4 that helps us for the graphics, and we have up to 4K resolution with 60 frames per second to support dual monitors. We saw two HDMI ports, so it is must obvious that we have two ports. Okay. So now comes, we have discussed what is uh, cloud computing. We have spoken about edge. We have seen that Raspberry Pi is a device of choice. Now we move to a concept called as cluster computing. Why do we need to build a cluster, right? As I am heading towards building a powerful edge computer, right? So so when we think about machines which help weather forecasters, they provide, they are engaged in billions of calculations. And to perform these type of operations, we need two things. One is you need to scale vertically. You need to scale vertically. Like you have a single server and you put in a more faster CPU, more RAM and faster connections, like I told previously. Or the next thing here is you scale up horizontally, where you split up the task and use multiple computers. These are the only two known options that we can explore. So, since which is the supercomputer series that is manufactured in India? So, our Indian supercomputers have which name? Indian supercomputers, Indian supercomputers, right? Have which name? Which common name I would say? Yeah, Param, fantastic. So these gray, like in my slide, these gray supercomputers were the one which were available in countries like United States, right? But what happened here is because of technology sanctions, it was not provided to country like India. We needed to it for nuclear testing and other simulations. So Central CDAC, right? They came up with our own Indian supercomputer, and it was called as Param, right? So, so this is the supercomputer approach, which is a very powerful computer, and it is used for computations like weather forecasting and all. But it is pretty costly. It is very costly to install supercomputers, right? So another thing that came up with when powerful desktops came into the picture, clustering was one that came into the domain, and we had Beowulf clusters, right? We could build a Beowulf cluster. This is still administered in most of the universities across the world, where they build a Beowulf cluster on Ubuntu, right? It came. Nowadays we have Kubernetes, which help us to do similar functions and distribute applications across many computers. So we are heading towards a cluster computer, right? Even with the software, there are two big problems, right? Especially with scaling horizontally, if you're on a budget, then each computer costs a bit of money, right? All of you agree. If you are going to build a cluster, we need computers, and computers also cost a money, right? So if you are going to build a cluster of maybe 10 to 15 computers, they will definitely cost a money. So what is the solution? The solution is something we call it as the Raspberry Pi Dramble, because a Dramble is a group of Raspberry Pi fruits, or it's a cluster, right? So we are going to build. This is how it looks. So if there are any students who are attending my sessions, or if there are uh, industry experts who would like to build a cheap uh, server based on cluster computing, right? This is something. Here we are having one, two, three, four, five, six. What we can say Raspberry Pis. They are connected to up to 8 we can go to a hub. Beyond that, it is preferred to go to a switch. We also get a 6 or 8 port switch, right? One among these nodes will work as a master and others will work as a slave, and they have a power connector. Instead of connecting individually, they have a connecting devices and all these facilities, and you can build a Raspberry Pi cluster. Function in Pi only, right? So as I said, it's a what you can say a tiny credit sized computer. It is cost effective, right? And it can give you more powerful performances like a desktop computer. It is cost effective, cheap, and definitely I built a Raspberry Pi computer at my home with less than around 7 to 8 thousand. I have which I use it to run some of my uh, code which I write for my papers. So if you think of a AMD Threadripper 3970X, which has 32 cores, and you compare it with a collection of Raspberry Pi 3 Plus, right? Here 32 core would cost you $1,899, and the similar collection Raspberry Pi would cost you 45. So there is cost advantage, and also the Raspbian operating system. Raspbian, I don't remember, but still I'll pose a question. Let us see whether anyone can answer this. Yeah, uh, try to write it here. Your Raspbian OS, right? Your Raspbian OS is based on which flavor of Linux? Raspbian, Raspbian OS, right, is based on which flavor? I don't remember which flavor of Linux. Raspbian OS, right? A popular operating system which drives your Raspberry Pi is based on which flavor of Linux? Yeah, Karthik Kumar Chaudhary has given a perfect answer. It is the Debian. When Linux became popular, there were many flavors like we had Debian, Mandrake, SUSE, and then our popular Red Hat, right? And so on and so forth. Mandrake, I don't know. SUSE migrated to system administration, and all those people would use it. And Red Hat got split into Fedora, which was the free version, and Red Hat became the enterprise with support from Red Hat Enterprise, right? Enterprise server based operating system. And the more famous that we all use for our machine learning and all is now that dominates individual users, right? Is Ubuntu. Right. So it is right. Karthik Kumar Chaudhary has given the right answer. So, so what we have studied so far: cloud computing, edge computing, and the significance of placing computational load on the edge of the network, and Raspberry Pi 4 and Raspberry Pi 4 as a cluster. We need to build it. All right. Now the next thing we call it as deep learning. So we had artificial intelligence during 1990s, and it was like, to tell you frankly, it was like a dead science. People said that artificial intelligence, by which we spoke of fifth generation of computers, is not going to take place because it's beyond our capabilities. So it was like a dead horse. And we had all this. We had artificial neural networks, right? We had all our regression, prediction, and all these things we had. It was like it had come, but it was a dead science. The pure artificial intelligence, like pattern recognition, right, and uh, deduction. We had some languages like Prolog and all these things, right? So it was like a dead science, and our person who framed that this Coursera course, when he was in the uh, Google Brains Lab, he came up with speaking of a scalable supervised learning, right? Which, when given some thousands and millions of rounds of data, right, could predict or could deduce something very reasonable. So came up with the concept of machine learning. So machine learning was a specialized branch of, or a subset or a specialized branch of artificial intelligence, and deep learning, you can call it as a specialized branch of machine learning, and they are based on the concept of artificial neural networks, right? And what is the goal behind them here is they use multiple amount of layers, and they take raw input and they try to identify devices. Like here in the diagram I've shown, with some raw edges, the algorithm is able to deduce that whether it's an elephant or a penguin, or so and so forth. So the power with deep learning here is like I had a older laptop i3, and I tested some images applying some deep learning on convolution neural network. The laptop heated very quickly. It gives a huge amount of green footprint, right? So these heat up the processes very quickly. The one that is more useful for image processing and all are convolution neural networks, right? They are based on similar like our multi-layer perceptrons, but they are not as full connected as our multi-layer perceptrons, right? And they are we have their optimization strategies like AlexNet and all, and they are useful. See, the only learning strategy that can defeat humans when the size of the image, when the number of images are used and huge, and we have to perform redundant searching or analyzing, then these deep learning algorithms are known to perform better than even humans. So I had done a small experiment. I work on data. I don't work on images. I don't work on uh, NLP, though those are not my immediate goals. I worked on a data. Now this data set had something like uh, 47,000 records, right? We call it as a small data set, or I can call it as a medium data set. There were two devices that I took for experimentation. One was my laptop i5, and it was based on 2.50 gigahertz, and I used Raspberry Pi B, right? And the most horrible task among all this was installation of deep learning. It took me around hours together to install this, and then I computed the time in seconds using the time module available in Python. So if you see logistic regression, we'll go for the complete data set, right? I will not even consider the adding of Gaussian noise. If you take complete data set, logistic regression. Now my question here is, if you see the table, right, why logistic regression is the fastest? Why logistic regression is consuming least time? If you look at the times column on both the categories, you see that logistic regression is the fastest. Just a quick word to the organizers. Can I have another 5 more minutes?
Yes, sir.
So, if you look here, the logistic regression consumes the least time. So, what is the advantage here is you can use it as a benchmark. Like when I try to optimize a deep learning, the goal of this paper, which is to be still published, I hope no one misuses it. It is to be still published. If you see that the third column where I've used selected data set with Gaussian noise, I've used the pipeline architecture. And with pipeline architecture, the amount of time in seconds I used was 49.9, or you can consider approximately 50 seconds. The same thing on a Raspberry Pi was 382 seconds, and it is incomparable to anything. Like uh, if you look at SVM, it uses 7,210 seconds, right? But with pipelining, it uses only 382 seconds. Can you see what is the manifold increase in efficiency? If you look at a deep learning artificial neural network, it used 2,425 seconds. So in this, in terms of SVM, deep learning, and in terms of a simple artificial neural network, multi-layer perceptron, right? SVM was competitively better, because though SVM gives support vector machine gives better results, in terms of time consumption, it is the worst performer. And of course, our logistic regression was a benchmark. It would be a dream to reach something here, but something better than deep learning was quite appreciable. So by this medium-sized data set, I tried to prove that if we take a machine learning algorithm, apply a pipeline architecture, put it on a device like Raspberry Pi or medium-sized data of 42,000 records, I can achieve computational time efficiency, which is superior to the normal SVM, as well as the deep learning and the normal neural network. This was one of the experimentations which I had done. So what is the future? The future, I feel personally, is distributed deep learning architectures, and it uses the distributed resource of a cluster. I just now told you how we can go for building a cluster. I did not take a practical session, but next time when I get an opportunity, I will teach you, I'll prepare a video, or I'll teach you how practically to build a cluster using Raspberry Pis, right? And we have softwares for these based on things that can manage these clusters in the master slave mode. This is the future which I look for, distributed deep learning, right? So the future I consider is deep learning, software pipelining, Internet of Things, cluster computing, and distributed computing. So these are my references which I used for the talk. So if anybody has some any things to share or ask, I'm open.